So let's now continue with the lecture on optical fiber communication. What we learned in the previous hour is that we are using fibers made from glass, weakly guiding, so very small difference of index between core and cladding, but that was the condition for low loss. So this material is provided as low loss. And about the dimensions, external diameter 125 micrometers. This is for standardization. We need sufficient cladding, and usually we do get enough cladding to suppress any tunneling through the cladding in the outside world. So we have good guiding. And the core diameter, we saw that we had some limitations for the core diameter. Now just to repeat what we said, the first idea was to have to avoid multi-path dispersion. The first idea was to use a graded index core. Using a graded index in the core allows us quite a useful communication rate, but this is not what the fiber could do. The fiber actually has much more bandwidth available. For 4 terahertz bandwidth, Shannon promises us a much higher capacity than we could get from graded index fiber. Where was the real reason behind the graded index fiber? The real reason was splicing. So this core diameter here was standardized at 50 micrometers because 50 micrometers could handle even mechanical splices, even various devices that were available, say, half a century ago. On the other hand, single mode fiber was already known at that time. Single mode fiber was one of the first low loss fibers. But the problem here is the core diameter of only 9 micrometers. If we have just 9 micrometers of core diameter, we have to have very accurate mechanical connectors, very accurate arc welders to splice these fibers together. So the single mode fiber was actually well known. The theory was well known, but in practice, fibers with much wider cores, much thicker cores had to be used because of the connection accuracy. So this was really a mechanical constraint, not an electrical constraint. Equations were known. The other thing that is also worth mentioning here is that the only efficient light source was a light emitting diode at those times. And LEDs have a good coupling efficiency, reasonable coupling efficiency of 1%, just for these fibers with thick cores. Thick cores and maybe also thick cores and maybe graded index profile. So these parts match together. So the transmitter we had available, the transmission pad we had available, all these components match together. All these were way away from the single mode fiber because the single mode fiber has a very thin core. And this very thin core, and further it also has much lower numerical aperture. Also, numerical aperture is twice smaller than the multimode fiber, and this means just 1/4 of the coupled light. So if we have a 10 milliwatt LED coupled to a step index profile single mode fiber, the coupling efficiency is 0.1%. So 1 per 1,000, 1 part out of 1,000 power. So from a 10 milliwatt LED, we can at best get 10 microwatts of guided power inside our fiber. So this discrepancy between LED and single mode fiber didn't go together. But of course, if we want to make full use of our fiber, we have to go to better sources, better light sources. Here, so better than the LED here. with better focusing capabilities, and also better modulation, and also more controlled spectrum. And of course, having also all the hardware required to splice these fibers with very small cores. This hardware did develop. Up to today, we have very good splicing machines capable of doing single mode with losses that are below 0.1 dB, splicing losses. In fact, they are not even observable, the splicing losses. So this technology actually developed, so we could get to much better use of our fiber. When we're trying to do a better use of our fiber, we get into problems with material. Those 4 terahertz are not that easily attainable, because glass changes a little bit its refraction index over our wavelength range. At the shorter wavelengths in ultraviolet, we have UV resonances. Here we have infrared resonances. And in the low loss region here, almost lossless, we can describe the refraction index of silica glass with the corresponding coefficients for the Sellmeier's equation for silica glass. This equation does not include losses. It only includes the real part of the refraction index. And this equation is a good approximation between 0.21 micrometers, so this is already ultraviolet, to quite far infrared 6.7 micrometers. In this region, the losses are low, and we presume that that's almost lossless propagation. This if we now enlarge this detail here in our region of interest, our region of interest is in here in our region of interest is inside here in this region here, say between 1 and 1.5 micrometers, where the losses are the lowest. If we plot now the phase velocity, this is this green line here. This is exactly the reverse of this function here. So the phase velocity here actually is increasing with increasing wavelength because the refraction index is dropping. But the group velocity is what counts actually. For communication, we are actually making narrow band communication, so our bandwidth is much smaller than the central frequency of our communication, and we should calculate the group velocity, so the velocity the pulses propagate in such a media. And all these resonances, ultraviolet and infrared, actually they are resonant circuits. They store energy. They store energy in the form of reactive power here. This reactive power is now actually slowing down our communication. And since the group velocity is defined as the derivative of omega over beta, we have now to be very careful when we are calculating derivatives over lambda, because the refraction index is also a function of lambda. So we should make the complete derivative. Making the complete derivative here, we obtain this red curve here. We see that the group velocity is the fastest around 1.3 macrometer. When this slope is stable, here the slope increases, here also the slope increases, but the slope is stable in here. And so here the velocity is, the group velocity is less slowed by infrared resonance as well as UV resonance. Here we get slowing down by UV resonances, here we get we are being slowed down by infrared resonance. Here the delay is the smallest. And we can plot this curve here now. So this curve here really about 2 times 10 to the 8 power meters per second. It seems quite a flat curve. It doesn't seem much of a problem. But the real problem of the waveguide is the optical fiber is that we have very long fibers. A fiber may be 100 kilometers long. 100 kilometers is 10 to the 11th power of micrometers, and wavelength is about, in glass, is about 1 micrometer. So this transmission path is actually 10 to the 11th power wavelengths long. This is a very long length, very long interaction length with the media, and that's the reason why this slope, although it is almost constant, it's quite a flat slope. You see here even the scale is slow here. This slope here causes problems, and we'll see the problems in our next slide now. If we calculate the group delay, is of course the length of the fiber divided by the group velocity. But chromatic dispersion, what does that mean? It means that this group delay, Tg, is actually changes over the region of wavelengths we are using. So we are going to get our pulses broadened by this delta t, that's equal to the constant of chromatic dispersion times length of fiber times bandwidth of our transmitter. And now this thing is already, it is very small indeed. But thinking about the 4 terahertz bandwidth, this thing is very large. So numbers become such that this thing becomes important. If we look at the curve of the glass is close to 0 and 1.27 micrometers. But at 1 and 55 micrometers, this may be 22 nanoseconds per kilometer of fiber length per nanometer of source width, of spectral width. And now if we look at sources, okay, it is not glass the only constraint we have. Glass, we had the curve for glass here. But now we are making a waveguide out of glass. And making a waveguide out of glass, also waveguide has some effect, although at least an order of magnitude smaller than the effect of glass. The waveguide actually, the longer the wavelength, the more field the waveguide has in the cladding, the less field in the core. While for shorter wavelength, almost all of the field is in the core. And this shift of the field from the core to the cladding also changes both the phase velocity and the groove velocity. So these two curves, red and green, subtract to get the blue line for the fiber. And here we have all effects included. So oscillating electrons and molecules of the glass, and waveguide transverse phase resonance, because this transverse phase resonance is standing wave. Standing wave also means reactive power, so stored energy in the waveguide, and this will also slow down our communication. And we have to deal with this blue line here. And the numbers now to remember are at 1.3 micrometers. Fibers are guaranteed to have almost zero dispersion. Well, the tolerances are that the absolute value is less than 2 picoseconds per nanometer times kilometer, absolute value, so in with both signs. So if we think now about a simple laser communication, having a simple Fabry-Perot laser with a bandwidth of 3 nanometers and 50 kilometers of fiber, and broadening, this gives us a broadening of less than 300 picoseconds, this broadening here. This broadening here, if we convert it into capacity, we are limited with the capacity with this laser and this fiber to 1.1 gigabit per second. Here, the bandwidth of the laser is much broader than the bandwidth of the modulation. Bandwidth of the modulation here is 1 gigahertz. Laser 3 nanometers. 3 nanometers is around some 400 or 500 gigahertz. So this is much broader. Using a similar laser with a similar bandwidth of 3 nanometers at 1.55 micrometers, where the losses are the low, the blue line here is quite high, is around 17 picoseconds per nanometer times kilometer. And this link here will be actually limited to 130 megabits per second, just because of the chromatic dispersion and of the bandwidth of our transmitter. So this is actually the next limiting factor we encountered. Before we had to deal with multipath distortion, we could handle that, but now we have distortion coming from the media, from glass, and from the waveguide. And these two distortions, coupled to the finite bandwidth of our transmitter, will decrease much the link capacity here. Even if we do the best possible things, so we use a separate, very narrow line laser. A DFB laser has very narrow line, measured now in megahertz, now in no longer in gigahertz, and an external modulator. So our bandwidth of the signal is simply equal to the capacity of the signal, because we have no noise added by our transmitter, just modulation bandwidth. If we calculate now this, if we equate this capacity on the other side to the dispersion here, if you calculate equate the dispersion, we can calculate the link length for various capacities. And this link length assumes a perfect transmitter here, bandwidth only defined by the laser, and fiber that has some finite dispersion. If we plug in numbers for 1550 nanometers, lowest loss, and dispersion of 17 picoseconds per nanometer per kilometer, then we see that at relatively low bit rates, this limit is far away. We can get to 1000 kilometers only over a transoceanic cable with many amplifiers, many repeaters in between. But already at 10 gigabits, this is 70 kilometers. So this is already the distance between two towns, the distance of a typical optical link using single mode fiber. At 40 gigabits, optics is useful already at the limit. Here, with the best possible transmitter and 40 gigabits, we can only get less than 5 kilometers away. And forget 100 gigabit Ethernet with simple on-off modulation. Here we cannot get to our receiver even inside the building. We may have more than 700 meters of cable inside the building. So here it's a real problem. Here we are still far away. 100 gigabits is still far away per second, is still far away from the 4 terahertz of available bandwidth. But already here the distortion due to chromatic dispersion is so large that it can no longer be used. Such communication. We have to resort to different solutions. Now, the most stupid solution is to do wavelength division multiplexing. We divide this capacity over several links having a lower capacity. So if we divide this 100 gigabits per second into 40 wavelengths having 2.5 gigabits each, we could reach easily 1000 kilometers. But the cost of this complicated analog transmitter is very large. So these are actual limits of the material we are talking here. What was the solution? The practical solution. There were many solutions, and not all of them were good or had any success in practice. If we look now at the solution was to modify the doping profile of the fiber, having a shaped infraction index profile, having a spike in the center of N1 of X, and having an even lower N1 than L2 close to the cladding. Such a doping profile may have a much stronger waveguide effect, and may shift our dispersion line from this. This was standard single mode fiber that had here at 1.52 have 17 picoseconds per nanometer kilometer, while down here we get to 0. And this fiber was called dispersion-shifted fiber because it has a smaller core of 8 micrometers. It was 8/125. ITU was also standardized as G653. This fiber was intended for transoceanic cables. The fiber itself did work as promised, but in practical use it was a disaster. Why it was a disaster, we shall see that later on, because of non-linear effects, not just due to the smaller core, but also due to the zero dispersion coefficient. The dispersion coefficient is not that it is a problem here, but this can be worked out by linearly processing this signal. If we get into non-linear effects, we can no longer remove intermodulation distortion, and that is a big problem. So, what is the solution today? Or either use standard G652 fiber. This is still alive, while this was dead in a few years. There was even a dispersion, so-called dispersion flattened fiber, G654, that never came to use, never came to manufacturing because it had many problems. Or use the standard fiber with the standard problems we had here. Or use so-called non-zero dispersion shifted fiber. Well, this dispersion coefficient is reduced from 17 down to perhaps +5 and -5. This is much easier to manage than the 17 here. So non-zero dispersion shifted fiber is a way in between, and connecting equal lengths of two such fibers in series, we can cancel out the chromatic dispersion completely without generating nonlinearities. These non-zero dispersion fibers were even designed with very large area cores, again to minimize nonlinear effect. This was large effective area fiber was the discussion. Yes, we had this was for new installations, for new transoceanic cables. We had non-zero dispersion shifted fiber because this one had terrible nonlinearity problems, while for existing links using standard G652 fiber, they developed also dispersion compensating fiber with a very, very large dispersion coefficient. So it will not fit on this graph here because it's much down here, the graph here, but with a slightly higher attenuation because this fiber has a very small and highly doped core with lots of germanium, and lots of germanium means lots of Rayleigh scattering. This is also a possible solution. So if we look at all possible solutions, now what we can do for new installation. For new installation, we like a transoceanic cable that's made with all new hardware. We put a series connection of a non-zero dispersion shifted fiber plus and minus. So the dispersion coefficient here almost cancels out. We do some fine tuning, fine correction here in the receiver. And transoceanic cable is designed as an analog transmission line, not to have any signal processing on the bottom of the ocean. This is a spacing around 50 kilometers, so at a transoceanic length of 5,000 kilometers, we may have 100 optical amplifiers, and these optical amplifiers are completely analog amplifiers. In fact, the erbium, the most popular erbium amplifier, has the bandwidth of 4 terahertz, and this is our specification for this line, 4 terahertz bandwidth. This is the reason why we use this number elsewhere. These amplifiers have very good performance, very good signal to noise ratio, so it is possible to handle a line with 100 amplifiers in series and no signal regeneration under the surface of the ocean. So this is the big advantage of having these very good optical amplifiers. Of course, in order to use such a line, we still have to limit the symbol rate on this line to 10 gigasymbols per second, or a maximum of 40 gigabits per second, multiplied by some more complicated modulation scheme. So we have multi-level communication, multi-phase communication, so QAM communication, and QAM using both polarization. We also do polarization multiplexing to get perhaps 10 times, at least 10 times the symbol rate we get the actual capacity of this fiber. 10 bits per second per hertz we obtain on a transoceanic cable. On shorter ranges, like an intercity cable of 100 kilometers length, here we may have just already laid down the standard G652 fiber, and we add new equipment in the receiving cabinet in the communication center here, that has first one optical amplifier to recover the signal level. But now we have the signal level, we have good signal to noise ratio here, but the signal is distorted. We use a spool of dispersion compensating fiber, a spool that's installed in the rack. So this has several kilometers of fiber, but this is just a box, say 15 centimeters aside, containing a spool of fiber. And since this fiber has quite some loss, we need another optical amplifier before we get to the receiver. Of course, this is in the complicated world. If we need not use the fiber to our maximum performance here, say if we are happy with 10 gigabits and 70 kilometers, then we don't need to do anything. There is nothing that needs to be done here. So here life is very simple here. So if we do in a local network, usually nothing is required. If we have just Ethernet equipment operating at 10 gigabits per second, it's not necessary to compensate for the chromatic dispersion of the fiber. There are other technologies also for chromatic dispersion compensation. One very complicating is to use a very long fiber Bragg grating. So in an optical fiber, it is possible to write a Bragg grating using an interference pattern generated by ultraviolet light, where ultraviolet light hits germanium inside an optical fiber, it slightly changes the refraction index of the glass. And so with ultraviolet light we can change the refraction index and we can write whole gratings using interference patterns. Of course, this grating needs thermal tuning to adjust its length so that the faster wavelengths actually reflect here and the slower wavelengths reflect here. We have to tune precisely along the length of this grating. We can have to tune exactly its period with thermal tuning, usually Peltier heaters or coolers along such a grating. So this can be done as a plug-in box that's adjustable by thermal tuning to compensate for any length of fiber on our link. So in place of the DCF spool, we can have something tunable. A more complicated tunable device is the Girard-Tournois étalon. This is actually a resonator, dielectric resonator, that uses two reflections, one of its front surface and one of its back mirror. And this device actually has a periodic group delay. A periodic group delay has slopes of in both directions, and this periodic group delay can be used to compensate not the whole frequency band here, the whole band of wavelengths, but to compensate, say, chromatic dispersion in a WDM system. In wavelength division multiplex, you can, of course, this the thickness of this étalon is selected to match the period of the WDM spectrum, so that we have exactly the same slope. We are using the same slope on each wavelength that is used on such a line. In order to connect this device, these are unidirectional device. This is just a reflection device. This is also a reflection device. We need a circulator, an optical circulator that can be built. This is also a component that can be built, but quite complex, to be used in our line to compensate for our line. So this is about linear properties. Chromatic dispersion is a linear property of glass. A linear property of glass and also of the waveguide. The waveguide has some effect, but usually the waveguide effect is much smaller than the glass effect. Besides linear effects, we should also remember that the cross-section, yes, and yet another linear effect I forgot here is that our transmission line, our single mode fiber, is really a two-mode fiber. We have two orthogonal modes, maybe horizontal and vertical polarization, maybe any other orthogonal couple of polarization. And these two polarizations do not have equal speed due to manufacturing tolerances. The most usual problem is that the core is eccentric. An eccentric core produces mechanical forces, and these non-centric mechanical forces cause birefringence, and birefringence causes polarization-mode dispersion. So two pulses with orthogonal polarization do not propagate at the same speed. For instance, here the pink pulse is faster than is slower. Actually, the pink pulse is slower than the yellow pulse here. Vertical polarization was faster than the horizontal polarization for this case here. So polarization mode dispersion is something that happens. It was not discussed. Polarization mode dispersion was not discussed before these issues were not solved. We had first to solve the single mode fiber, the multimode dispersion. We had to solve the chromatic dispersion problem, and once these things were solved around around the year 2000, we finally became aware of this problem. Before we were not aware of this problem. This polarization mode dispersion may be a big problem. So with old fibers that may had an eccentric core, this resulted to that this is polarization mode dispersion is a totally random distribution. That's the reason why the optical fiber does not maintain polarization. But this random distribution caused about 10 picoseconds per square root of kilometer. Square root of kilometer, square root of length is because of the random nature, because we have a sum of random contributions. 10 picoseconds is quite a big number for say 10 picoseconds is equals to a symbol rate of 100 gigasymbols per second. So this is already a disaster here. So this is 100 picoseconds for 100 kilometers. So this is 10 gigasymbols per second, and this is just 1 gigasymbols per second. So we are very limited to such a fiber with the distortion caused by the two pulses having the different delays here. After the year 2000, they noticed, this problem was noticed, and the countermeasure was very simple, but it had to be done during fiber drawing. On the drawing tower, the fiber had to be turned around this axis at about 5 turns per meter length of cable, and in this way the eccentricity of the core is no longer always on one side of the fiber, but the eccentricity of the core makes a helix around, makes a helical path around, and this helical path actually evens out the mechanical forces, evens out the polarization mode dispersion, and we can reduce the polarization mode dispersion by the factor of 100. So 1 picosecond now is negligible today, and 10 picosecond for a very long transoceanic cable is may become apparent at the highest rates at 100 gigabit or even more at 400 gigabits per channel of wavelength division multiplex. The problem, this was not noticed before, is also that this polarization mode dispersion changes with time, and changes with time very slowly, weeks or even months. So you may install a link that works perfectly for a few months, and then it fails, then it drops out. And why it drops out? It drops out because of polarization mode dispersion has changed in a few months of time. That's the reason why this polarization mode dispersion was not noticed before. So this is also a linear effect, a completely linear effect, but something we forgot. And also I forgot in this lecture to mention it. I said we have linear chromatic dispersion. Yes, polarization mode dispersion is the smallest of all three. If we take multimode dispersion here, if we have multimode dispersion here or here, multimode dispersion, we have chromatic dispersion here. We have polarization mode dispersion. Polarization mode dispersion is not the smallest, but it should not be neglected. It has to be considered, especially when we solve this problem. When we solve this one certainly is a limiting factor, and it's a nasty one. We may not see it in a few days of measurements. We may only see it after a few months or even years. Now, the last problem to deal with today is the non-linear effects in optical fiber. What happens in an optical fiber? The cross-section of an optical fiber is very small. It is 125 micrometers of cladding, and the core of a single mode fiber, whatever special version of this fiber is, so all these are similar in the meaning of the dimensions. All these have the same size core. And the power density in this core is extremely strong. For instance, if we start with 100 milliwatts, if we consider the power density is 1.4 gigawatts per square meter, or 140 kilowatts per square centimeter. So this is a very, very, very high power density. It's much higher than we have in electrical cables. Also, the electric field is very large if we take the impedance of free space, if we take the refraction index of the core. It's also extremely high. This figure is already close to the breakdown in air. But we should not forget that this is in glass. 8.5 kilovolts per centimeter in glass, not in free air. What are now the non-linear effects we can see? Well, something we didn't talk about. What is the maximum power we may have in fiber? With 1 milliwatt of power, we may already see a non-linear response in our fiber, so we can already have mixing products, unwanted mixing products in our fiber. At 10 milliwatts, we may already burn our connectors. There's a transition from glass to air and from air to glass. And if some dirt accumulates, that dirt may cause a breakdown of this 8 kilovolts and may burn the connector. A burnt connector can only be replaced. It cannot be repaired. You can only replace the burnt connectors. So the maximum safe power we have for connectors is 100 milliwatts, and this is with careful connector cleaning at each connection, of course with power off. 1 watt is the maximum power in fiber. So with 1 watt is the maximum the fiber itself, the silica glass here, can tolerate. And with 10 watts of fiber, we already get to the melting of the core. The core will melt. Will cause bubbles here, and will completely disrupt the communication. So we will destroy our optical fiber cable if we put in 10 watts of power. Let's see now what are the non-linear effects we can expect in our dielectric. The main common point of all non-linear effects is electrostriction. Electrostriction is actually the square effect, proportional to the square of the electric field, because forces grow with the square are proportional, forces, mechanical forces are proportional to the square of the electric field, and when we squeeze the material is the electric constant with forces, the electric constant will increase. This is known as the Kerr effect or electrostriction. If we have our material with the strong built-in electric field, then this electric field sums with the externally applied field, and we may have the linear Pockels effect. That's electrostriction plus internal electric field. This does not happen in glass, but it happens in crystals, in some crystals like lithium niobate. So in silica fiber, with most of it being silica glass with some germanium, the internal field is 0 and N1 is 0, so we only have the square effect. It's much more convenient to rewrite this equation in terms of power density S, so this is watts per square meter. So we have N0 for the basic refraction index, and N2 is this refraction index coefficient. It does not mean cladding N2. Here N2 means the second order effect here. N2 times S, where this N2, N1 is 1.646 for silica glass, N2 is very small, is 10 to the minus 20th power of meters squared per watt. Multiplied by watts per square meter of S, we get the change of the refraction index. Minus 20 is a very small exponent here. But if we go to the previous picture, we have 10 to the 9th power of watts per meter. So this is 10 to the 9th power, this S. And we have 10 to the 11th power of wavelengths per 100 kilometers of fiber. So 10 to the 11th power and 10 to the 9th power, this minus 20 cancels out. And these things becomes observable, becomes also a nuisance or something useful the way we are looking at it. But we cannot neglect nonlinear effects at high power communications, especially when we are above say 1 milliwatt or above 10 milliwatts here, above 1 milliwatt, 10 milliwatts. Here we should no longer neglect nonlinear effects. What happens in glass? There are many different effects. Primarily the lone electrostriction may cause effect, the Kerr effects, but also various additional mechanical resonance inside glass may make these effects. For instance, our light may generate an acoustic wave inside the glass, propagating at 5.9 kilometers per second. The same wave now reflecting off this diffraction grating here, exactly in the same backward, will be reflected back and shifted by frequency, since this acoustic wave is traveling in the direction of light. There will be the Doppler shift will be downwards. We can calculate it, and for our 194 terahertz of frequency, we will calculate that the frequency shift is around 11 gigahertz. This is the Brillouin scattering. It's only in the direction backwards, because this diffraction pattern will only reflect light backwards of just one wavelength, so it's very narrow band. And this 11 gigahertz is given by the Doppler shift due to the velocity of the acoustic wave. The real problem is that Brillouin scattering happens already at very small powers, just a few milliwatts, provided that this optical signal is narrow enough. Well, most optical sources have a broader spectrum, so Brillouin scattering does not apply. But if we have a very good quality optical transmitter with very narrow carrier, then Brillouin scattering may happen. In fact, Brillouin scattering was happening in analog television distribution links. There it made the problem. Otherwise, Brillouin scattering today, it's no longer a nuisance because our transmissions are broader. It's too narrow to be an amplifier, but it can be used as a sensor, so it has some application. On the other hand, Raman scattering only happens at very high powers, but it's very broadband. It happens in both directions, so we can make a Raman amplifier, a laser amplifier, shift it around 13 Hertz below our pump frequency. And here we can make an amplifier provided that we have this enough power, 600 milliwatts. Well, this can be done in a fiber, but here it's very hard to use connectors. It's very difficult to get lasers for this power level. So also Raman scattering, you can make Raman amplifiers, also very low noise, also for long distance communications, but they are very expensive because the powerful laser here you need is very expensive. It needs not be narrowband. Raman may have a reasonable bandwidth lasers. Finally, we have the electrostriction on its own that increases the refraction index. Well, it causes self-phase modulation. Self-phase modulation is already observable at line length of 1 kilometer and 100 milliwatts of power. This 0.15 radians is already observable of self-phase modulation. Since our receivers are usually not sensitive to phase, this does not matter. Self-phase modulation does not matter. It was thought several years ago, say 30 years ago, that soliton transmission using the subtracting from linear dispersion, linear chromatic dispersion, the nonlinear effects of the refraction index, could keep pulses of a certain shape. That was called the soliton shape, and soliton transmission was considered as soon as 30 years ago. Many laboratory experiments were done. Lots of money were put in the experimenting with solitons, and no practical result came out. So this was something too difficult to make. So there was no useful use of self-phase modulation. Now, today, the real problem is cross-phase modulation, because cross-phase modulation causes four-wave mixing. This is a new term coined in optics, because radio engineers have been calling exactly the same thing for 50 years, intermodulation distortion. Intermodulation distortion is a nasty effect, because from two frequencies, two signals at two different frequencies, it generates additional signals at additional frequencies. And these additional signals may fall on other frequencies in use by other communication on other channel on a huge wavelength division multiplex on a transoceanic cable. So this is real interference. They cause real interference. How does four-wave mixing happen? Well, intermodulation distortion is much better term. Is a third-order distortion. If we have a non-linear n, and this is already proportional to the square of the field, multiplied once again by the field, we have field to the third power. So it's a cubic nonlinearity. So from frequencies f1 and f2, it will generate two interferences at fa and fb, and these interferences are all of the third order. So this is third order intermodulation distortion. In electronics, we are used at low frequency to have any order of distortion. But in optics, only those frequencies that happens to be close to the signals have enough phase matching to actually grow. Because here the nonlinearity is distributed along the transmission line, and in order to get these mixing products, we need phase matching between all frequencies involved. In fact, that's our countermeasure. If you calculate the powers of the interference, the power of interference Fa and power of interference Fb, Pb, they are proportional to the third power of the input power, depending how they came from, divided by a calculation constant. This is the square of the intercept point power. Intercept point, third order intercept point. This is quite a common term in radio. It's almost unknown in optics, but it can be easily calculated. It depends on the wavelength, on the effective area of the fiber, on the nonlinear coefficient of the fiber, and on the effective length of the fiber if the fiber is very long. If it's just short, the fiber here is only length. But if attenuation plays a role, and phase mismatch plays a role, then we calculate here with effective length, and effective length is much smaller than the length of the fiber, because when the power decays, there is no longer nonlinear interaction, and if there is phase mismatch, also the nonlinear product is much smaller. So this here now is a very, very theoretical discussion. Now let's see what really happens in practice, to have a practical example of a transoceanic cable. How the transoceanic cable was made 30 years ago, and how it is made up to today, until how it is made contemporary right now. So 30 years ago we had the dispersion-shifted fiber that had, well, a small core, but it was not a real problem. The real problem was dispersion equal to 0, so delta beta also equal to 0. This effective length was very long. Effective length that comes in here. A very long effective length means a very low intercept point, a very low intercept of 20 milliwatts. If we put all the numbers about the glass in here. And this is a very low intercept point, but because at 20 milliwatts, this means that our interference is already the same power as the useful signal. So we should use powers much less than 20 milliwatts in such a cable. In fact, these cables could only do 4 channels WDM at 2.4 gigabits per second to span the ocean just with 10 gigabits per second. This was the technology 30 years ago because of this inadequate fiber. And if you calculate the power here. All links are considered always at 1550 nanometers, always with the same kind of glass and with the same bandwidth. In fact, for these old cables, the selection of the individual 4 wavelengths, 4 channels, was very critical in order to have the most of this interference out of the band of these channels. And with 4 channels was already difficult. With 8 channels it was impossible. How do we do it today, or say 10 years ago? We use non-zero dispersion-shifted fibers for the cable. We have quite a significant beta at the channel spacing of 100 gigahertz. We have effective length of only 400 meters, and this is that makes the difference. The effective length here is much shorter because these contributions of each individual maxi do not add in phase, but add in a spiral. Adding in a spiral instead of a straight line, we get a much shorter effective length, and the intercept point is much higher, is 33 dBm. This is 2 watts, and in fact here we can use much higher powers for our individual channels and have controlled some, but controlled intermodulation distortion of such a cable, so we can reach 4 terabits per second and even more. Now the record is well beyond 10 terabits for a transoceanic cable. Much higher than that, but using much more appropriate cables than we did here. So this is a short, today it was a short introduction over all of the limitations and tricks of optical fibers. I didn't say anything today about the corresponding terminal electronics, also because we I didn't explain semiconductors yet. There's lots of semiconductor technologies here, a little bit different from the radio technology. Today I just wanted to explain the fiber and the limitations of the optical fiber. Where are the limitations of the optical fiber? That's all for today.